Okay, and we're on. So, thanks a lot for coming, guys. We're here to present our research, and it's on something called a digitally trimmable voltage reference. This is something me, Dr. Christoffersen, and Dr. Rossi, we've been working on all summer long. Okay, so first of all, before I explain too much, why exactly are we doing what we're doing? What's the motivation behind all this? So there are two demands in the world that we're trying to address here. There's, first of all, a demand for electronic devices that don't take up that much power and also don't take up that much space. And there's another demand where these electronic devices need to be really accurate. So the devices that would meet these demands are like implantable sensors, as you see here, and also temperature sensors. So these are things that would that our research is helping to develop towards. So in order to get all these things here, there's a fundamental circuit that makes it work that's called a voltage reference. And the objective of this research is to make sure the voltage reference doesn't use that much power, it doesn't take up that much space, and is also really accurate. So just a little background on, yeah, there are some side issues here, but that shouldn't be important. The fundamental question is, what exactly is this voltage reference? So it's an electronic device where if you put power to it, then at a certain point you'll end up with the same voltage regardless of your supply voltage variations. And Dr. Rossi, we're on slide 6 now. And not only does it give you the same output at, like, say, room temperature, but this output applies towards all temperatures. So from, like, say, minus 20 degrees to plus 80 degrees, ideally a voltage reference would get you an output that doesn't change as your temperature changes. So the way to use this voltage reference would be like in analog to digital converters, where you have a reference voltage in here, and you compare it to an analog voltage. And from this comparison, you can then work out the digital code that the analog voltage represents. So essentially, it's an analog to digital converter. And also, the digital temperature sensors, they work the same way, where instead of just any analog voltage, you have a voltage that would increase with temperature. So the digital code that you end up getting represents temperature. So smart temperature sensors use voltage references. So that's what it is, and this is how to use it. Now, where did it all got started? The very first voltage reference, the integrated circuit at least, was invented by Widler in 1971. And what he did, he combined two parts. This red part here would be a part that would increase in voltage as temperature increases, and the blue part here would be a part that decreases as temperature increases. So by combining these two parts and having them sum up to be the bandgap voltage of silicon, he could work out a way to have a voltage reference that does not change with temperature. So this voltage reference actually is a huge improvement over what existed before. They used to use Zener diodes. So compared to the Zener diode of a voltage drop of 6 volts versus this 1.23 volts, that's an improvement. However, over time, we wanted smaller electronics and electronics that don't take up that much power. So now, if we wanted to do that, there's a problem. These bandgap voltages traditionally can't be less than 1.23 volts. So if you wanted something that didn't take up that much power, it's going to be a problem. Another problem is for lower power, you need larger resistors in your design. And in terms of integrated circuits, if you do use large resistors, that's going to take up a lot of space. And that doesn't help if you wanted something that doesn't take up that much space, like a small footprint you see here. Also, these resistors, the larger it is, it's actually really inaccurate in your integrated circuits. And so the larger it is, the more inaccurate it is, and you end up having a design that doesn't work the way you wanted it to work. So that's the problem with the original bandgap integrated circuit. What came after that? That resistor problem with integrated circuits, they ended up finding a way to use MOSFETs only. So instead of having like this structure you see here, circled by my mouse, it would generate a constant current to this point of the circuit here. And what they normally do is they just put a really, really large resistor at this point, and you end up with a really constant current. What Ogui found in 1997 was, instead of having that resistor, just simply design a transistor to work at exactly that voltage. And there you go, no more need for resistors. You can have circuits that are a lot smaller and a lot more accurate. And also, in at least 2009, there were new threshold voltage designs that were, new voltage reference designs that were based on the threshold voltage and not the band gap voltage. So fundamentally, that allowed you to have an output. It allowed you to have an output that was smaller than 1.23 volts. So these things actually solve the problem of you wanting low power and not taking up too much space on your integrated circuit, and at the same time be more accurate. These designs were based on, because over time we needed less and less power, more of the recent designs you operated in weak inversion. And what that is if you take a look at the transistor here, this P-type material, in theory, all of the P-type material would have a deficit of electrons, but there's going to be a minority of electrons, minority of atoms, that actually have an excess of electrons, so that if you apply a positive voltage potential at the drain here, it's going to attract a negative electron here, and you'll still have current. So what that really means is if you have 0 volts at the gate, you're still going to be able to have current flow if you have a voltage potential between the drain and the source. So a lot of these designs, they operated from weak inversion. Now, there is a problem with some of the recent designs. First of all, in our standard equations, our weak inversion behavior and our strong inversion behavior are accurate. So strong inversion is when you have a really strong positive potential here, pulling those negative electrons to form a really well-defined channel. So in terms of our standard equations, weak inversion operation and strong inversion operation are described accurately. However, it doesn't show here, but in 2005, one researcher found that actually, if you wanted the low power you want and also not take up the chip space you want, you're better off working from a weak and moderate inversion. So moderate inversion is this area in between where you have a half-defined channel. So looking at slide 17 here, okay. Now, the problem with moderate inversion is if you look at a textbook, like Gray's textbook here from 2001, moderate inversion actually, there's no equation that tells you how it works. It's well defined in weak inversion and strong inversion, but moderate inversion is just some unknown. Now, the simulators, what they do is they actually model it using empirical data. So really, they would test a transistor in the lab and then find out what these results of the tests are and then try to guess a certain curve behavior. And so for that reason, anything working in moderate inversion, you can't rely on simulation results. And also for that same reason, most designs, they don't use moderate inversion. So by not doing that, they're missing out on the optimal power and area usage of the chip. So another problem with, this picture isn't quite what I originally intended, but just bear with me. So process variations, they still affect these voltage reference circuits. So these voltage reference circuits all use MOSFETs, and they're still affected by process variations. Like, for example, in 2009, this person's circuit, he designed it for the ideal performance, where there's no change in temperature there's no change in voltage as you change in temperature, a 0 temperature coefficient. But when he actually measured one chip, he got some curvature here that represented 7 parts per million per Kelvin change. And another chip had an even worse curvature here. So really, the problem is the performance isn't consistent. Okay, so you design for something, and you might end up with something else. So these are two problems that exist today on slide 19. The standard design equations might not be right, and the process variations still affect the results that you're designing for. So how does this research solve these two problems, right? Just instead of using the standard equations to describe the MOSFET operation, we don't use the standard. We use something called an advanced compact MOSFET model, or ACM model for short. And really, that's just a single set of equations, no matter whether you're weak, moderate, or a strong inversion. It's still gonna, you still have the same equations, whereas in the original, you have two different sets of equations for weak and strong inversions, and they're treated as two separate things. And now this is all based on physics, so the advantage of that is all the behavior can be predicted, rather than having to test your MOSFET in the lab and then plot your data and try to guess a certain behavior. Now, in terms of process variation, that's how we propose to solve it. Is we're going to have a way to change certain parts of your of the circuit itself, like the size of the transistors and the currents going through it. And as you'll see later, by changing these properties, we can actually fine-tune the circuit so that no matter what your process variation is, you will still get the performance you want. Okay, so that was the background and where we are now. Okay, and so before any the design can be done, there's got to be some fundamental things that we have to know. So first of all, how does the ACM model work? So if you look here, the ACM model, it describes the current going through your transistor like this, as a function of your forward current minus your reverse current. And it models it by this equation here, where you have where you're relating the size of your transistor with something called a sheet-specific current and a forward and reverse inversion coefficient that represents these two currents here. Okay, what exactly is that sheet-specific current? It actually relates to a lot of the physical properties of the MOSFET transistor itself, like what's the electron mobility, oxide capacitance, all those things. You don't really have control of that in your design, but you have to know it, or else you can't design the chip. Okay, and it models the saturation. It defines saturation by the majority of the current being in the forward direction. So what saturation really is there's going to be a voltage potential at the drain and source where even if you increase that potential, you're not going to get more current. So the current's essentially saturated. So by that operation, it's described by these two equations here. And now you might be wondering, how exactly do the forward inversion and reverse inversion coefficients relate to the structure of the transistor itself? And the ACM model, it describes it like this. So how it works is if you have a certain forward inversion coefficient, you would put into this equation here, okay, and then the result of this equation relates to the gate, the threshold, the source voltage, and so on. And so what these equations imply is that your forward current is dependent on your source voltage, and your reverse current is dependent on your drain voltage. Generally, you would have a low source voltage, and so your forward current will be dominant in your transistor. Okay, and these same ideas, they apply to PMOS transistors. So the only difference is instead of being with respect to ground, you have everything with respect to the higher voltage potential at the bulk here. Okay, so I did tell you, the ACM model, no matter whether you're weak, moderate, or strong inversion, you're using the same equations. So how is it defined in the ACM model? So here's weak, moderate, and strong. And all the ACM does to differentiate these regions is just having a different value of your forward inversion coefficient. So so obviously here, no matter which number you use, these same equations apply. So it's a single set of equations for all regions of operation of your MOSFET transistor. So that makes your engineering design a lot easier. Now, one more thing that you need is, in order to design, is you need to know your sheet-specific current and your threshold voltage. So the sheet-specific current isn't something you can just grab out of the spec sheet. There's got to be a way to extract that value somehow. And so I followed some instructions by this author in his book here, and he's one of the guys that invented the advanced compact MOSFET model. And if you do ask me about it, I'll show you how exactly I did it. It gets pretty involved, and so I don't want to be too excessive on the details. And also the slope factor, we have to calculate it too, and that's also another involved calculations that involve the parameters I've extracted and the spec sheet values. So I'll only tell you if you ask me about it. Okay, so now on slide 31 here, this is the last fundamental thing we need to know. First of all, how do we even get constant voltage out? So if you look at the structure here, you've got a current going through a transistor where the drain is connected to the gate. Right? By the ACM model, it relates the inversion level with the gate and the threshold voltages like this. Okay, so now from the from the parameter extraction that we had before, we found that the threshold voltage actually does decrease in the linear line. And the thermal voltage, without doing any extraction, it would increase linearly because all it is really just KT divided by Q. So as T goes up, your thermal voltage would increase linearly. And because of these linear characteristics, then you can express your threshold and your thermal voltage in terms of temperature. So what's really going on here is this graph here implies that at 0 degrees Kelvin, you would have the maximum possible threshold temperature. So I'm a threshold voltage. Now, so that means all threshold voltage after that can be described in terms of this maximum possible threshold voltage here. So all this term is really is just the expected drop in threshold as you reach 300 Kelvin, and then this is just to relate everything in terms of temperature. So essentially, what I have here and what I have here are identical. So now, now that the equations lay out that way, it's pretty clear. The way to make sure that things don't change with temperature is get rid of the temperature-dependent terms in this equation. So how do you do it? You do that by having your gate and voltage the same as your threshold voltage at 0 Kelvin. And if you do that, you end up with this expression where the temperature terms cancel out. So that implies that there is a specific inversion level or operation of your transistor that would get you these conditions here, and that in turn would make sure that these cancel out, and so that way you would have a voltage reference that doesn't change with temperature. So that's the very fundamental thing that we needed to know before design is done. The problem is random process variations still affect the transistor. So their threshold voltages aren't going to be the same at 300 Kelvin. So to accommodate for that, it's clear that your inversion coefficient here needs to change so to account for any changes in your threshold voltage so that you would still get your output that doesn't change with temperature. So how exactly would you change the inversion coefficient? If you look back here at the ACM model, how it describes everything, you could either keep this one the same and change your size, or keep the size the same or change your the amount of current going through your transistor. And by doing that, you can adjust to compensate for the fact that your threshold is different and get the constant voltage output you want. Okay, so that's the very, very basic fundamental things. You can't, without knowing that, you cannot do the design, right? This is the design itself. Before we design, first of all, we had to compare what did everyone else do. And so we're going to try to do better than what's the next best performing circuit is. So if you look at this chart here, the best performing circuit worked at 7 parts per million per Kelvin. So we're going to target something better than that, 5 parts per million per Kelvin. And we have it work from at a commercial range, pretty much. So it's better than that. So we're over-designing it so that we're guaranteeing that for a commercial range, you can still have the performance the performance that you're looking for. And evaluating the amount of power that the other circuits have taken, we want to minimize that. At least get the power the same or less. So that's the design goal. Okay. Now. How do we implement this? How do we implement our general design? As you see here, we do need a constant current going through your transistor load, right? So first of all, you got to have some way to make a chip that makes that current, okay? Then second of all, you got to have some way to either change the size of the load or change the amount of current going through your transistor because you either change your I or change the size to change your inversion level to get the constant current. Okay, and we do this all by having transistors, really small transistors that divert current. So, like for example, if you turn this off, no current goes through here. If you turn it on, there will be current. So essentially, this is how we control the size and how we control the amount of current going through the load. Okay, so the design starts on right here, where you have a constant current. Okay, so how exactly is this current generated, right? At its most basic level, that current source consists of these 4 transistors here. Okay, and these 4 transistors are designed using the ACM model like here. So the first step is you have to decide on a current and then assume every single branch, all 3 of these branches have the same current. And then using the ACM model, so we decided that the current was 0.6 nanoamps. Okay, and so using the ACM model, from this configuration here, we can find out what exactly is generated here, what voltage is at this point here at the source of N2. And from there, once you know that voltage, then you would design these transistors precisely to work at that voltage that you've obtained before. And essentially, in doing all this, you would ensure that every single branch conducts the current that you designed it for. So essentially, that's how to design a constant current source. Okay, and these are the resulting sizes of the transistors. Okay, so now I guess I jumped too far ahead. But now you see these three branches, they conduct the identical currents. How do you have some structure that conducts identical current? We use something called a PMOS current mirror. So essentially, if the gates are all connected to the same thing, they're going to all conduct the same current. Okay? And another thing we needed to make sure was no matter how much this changes, your supply voltage, no matter how much it changes, you would still be able to have more or less the same current flowing through. Because there's a chance that if this changes, the amount of current change would significantly affect everything else. So the way around that is to use a cascode circuit. And so this is an NMOS cascode. And we also have another cascode to make the power supply rejection even better. So, this whole structure here in blue, that's another one of your cascode circuits. Okay, and everything was designed precisely to use as low voltage as possible. So that's how we're keeping our voltage at a minimum. Also, what we need here in order for everything to work, like this structure is great. But the problem is, what could happen is, like, say if your voltage supply changes from 0 volts to 1 volt, okay? If it does that, what could happen is not enough current gets generated to this NMOS structure below. And this NMOS structure below is what makes everything work. So if there's not enough current and it doesn't work, then you've got a useless circuit there. So what we included is a starter circuit so that as this changes from 0 to 1, you will have a temporary path for the current to go to the ground into, and then have the current build up enough so that by the time you have a high enough current, you can turn off the starting signal and then have enough current go through the NMOS structure below and just guarantee that everything works. So the rest of the circuit, it uses this current reference by copying the amount of current. It does this copying by basically extending these red and blue lines to other PMOS transistors. So whatever this conducts, those other ones will conduct too. And that's what this means at slide 48. Okay, so as you see here, there's going to be some thing that you have to do to change the inversion level. Now the next question is what's the least amount of inversion level you have to change to get the performance that you want? Through some long, complicated derivation process, which I'll show you if you do ask me about it, we found that the minimum change in inversion coefficient was 0.35 or so. And that corresponded to about 6 transistors. So that means there's going to be 6 transistors here that switch the current and 6 transistors here that change the size of the load. Okay, so now looking at that structure, so that is this here on slide 52. So what I have circled here, this is the constant load part, which corresponds to here, and then you have a minimum fixed current, okay, and a maximum, and then you can switch it up to a maximum level of current. And what this corresponds to is an inversion coefficient that would account for the worst possible things that could happen if you make the circuit and you undergo some random process variations. So it may not be obvious, but what I described before, this inversion level corresponds to the moderate inversion level of operation. And this is really important because it all works in moderate inversion, we can't really rely on the simulation results, which will come later. Okay, and so the sizing of all these transistors is based on the minimum switching current that goes through the structure. So we did decide based on the amount of leakage of these transistors to have one bit switch at 9 picoamps and all the other bits switch at a certain multiple of that. Okay, now looking at the load where you can change the size of the transistor, it looks like that. So there's going to be a fixed current and a part where your transistor can actually change in size. Okay, and so it changes in size by, like, say, if you activated this transistor here, your current will be diverted and it will skip part of the load. And essentially, that's the changing in the size part. So the first question I would ask if I saw this was, how exactly did you determine the amount of current flowing through the load, right? So we actually looked, evaluated, well, it's not circled correctly because we're not using the right format. But anyway, we evaluated based on the junction leakage. So in the transistor, there's going to be the equivalent of a reverse bias diode between the drain and the bulk and the source and the bulk. And we looked at every single transistor, found out how much they leaked, and also took into account of the off current of the trimming transistors. Like, say, if there was 0 volts here, there's still going to be some leakage current that flows down here. And we evaluated that to be about 4.4 picoamps. And based on that, we worked out the minimum current that can go through everything is 0.74 nanoamps. The problem with that is our estimates of the leakage of current might not be correct. This is actually based on simulation results, and we're not sure if we could have relied on that. So we chose something higher to have some sort of a safety threshold, and we chose instead 1.2 nanoamps going through this entire structure here. Okay, that's a really tiny current still. Now at slide 57, what we have is how did we decide on the size of this transistor? That was an arbitrary decision, right? So we actually decided based on the drain source change of 32 microvolts, and this represents the change of inversion level that's a lot less than the minimum. And if you have that change in inversion level a lot less than the minimum, you actually end up getting still being able to get the performance that you're looking for. So that's what we're going for here. Okay, so that is the general implementation of the circuit in a nutshell. Okay, now, so we're trying to get from point A to point B. We started on engineering design, and what we want is the chip. So what are all the steps involved, right? First of all, let's review that engineering design. It is in a separate file here. So I apologize for the technical difficulties, but I'm going to try my best to make sure this all works. Okay, so what we got here, this is the entire circuit. This is the PDF, by the way. And so what we have here is the design current source. And that current source gets copied over to the part where you can change the size of your transistor. And then you're changing the size so that you ensure that your voltage output stays the same no matter how you change the temperature. And just in case you're not sure which country this is made from, it was all made in Canada, right? So anyway, now that current gets copied over to the other structure where you're changing the amount of current going through your load. So this is what it all looks like. It's just all 6 bits here, and then you're controlling the amount of current into a fixed load to make sure that your voltage reference output doesn't change with temperature. Okay, so that is the design in a nutshell. So design check. Right now, one thing we have to do before we make the chip is we have to tell the fabricators how to make the chip. And this telling them how to make the chip is something called a layout design. Okay, so what we have to consider in the layout design is we have to, there's going to be a lot of random things that happen in when you make the layout. And so we have to balance these random things that happen so our chip doesn't get affected as much. One technique to balance this is to use unit transistors. And the reason for using unit transistors is we're accounting for diffusion here. And by that, I mean this. So what you have here is what you see in the schematic. What you'd have here is what you'd see in a textbook. And then if you rotate what you see in a textbook in a bird's eye view, this is what you'd see when you're doing the layout design, and that actually is important to know because, like, say if you in your original design you design for a certain width, like from between these two red lines here, and you design for a certain length between these two green lines. Because of diffusion, when you make your chip, your width will actually be a little bit wider than you designed it for, and your length will actually be a little shorter than it's designed for. And so now, because of that, the performance of your circuit will be affected. Now, say, for example, there's no unit transistor. You don't use any unit transistors, and in your design, you got a small transistor and a big transistor. So obviously, the small transistor is going to be affected by the diffusion a lot more than the big one, right? So if you did use unit transistors, like say split this into 2 parts that are all the same size, then everything gets affected equally by the diffusion itself. So for that reason, it was really important to use unit transistors. And another reason to use unit transistors is in the chip itself, there's going to be sections where it's going to be hotter than the other sections. So like, for example, this part's hotter than this part here. So the hotter part, M1, it's going to diffuse a little more, and the colder part, M2, is going to diffuse a little less. And that's going to affect the performance of the chip because not everything works the same way. So the way around that is use unit transistors again. So if you did split this into two separate parts, put one part in the hot side and the other part in the cold side and combine them together, then the effects of diffusion would be balanced. And by doing this, this is one of the things that we must do for fabrication, for the layout design anyway. And another thing we need to ensure was dummy transistors. Now, we have to make sure the environment of all your transistors are identical. What happens here is the drain of M2 sees the source of another transistor here. So by seeing the source, basically the electrons here will repel the electrons in a certain way that you can't really describe with equations, right? So if you did not have a dummy transistor here, what M1 sees here, it wouldn't be the same as what M2 sees here, and you will have what you end up with is really inconsistent performance. So for that reason, we use unit dummy transistor too. And the last one, probably the most important, is we actually just use a bunch of standard designs. We didn't really customize too much on the layout, so it's just a way to, if some company wanted to use our chip, they could save time and do it cheaply. Okay, so I've been explaining what the layout is, but you guys haven't seen what it looked like yet, right? So let's take a look at what that looks like. So, okay, what you see here in this picture, picture number 93-5, that is, okay, hold on a second. Let me plug in. So this is the complete layout design. That circuit diagram I've shown you before is all represented by these PMOS transistors and NMOS transistors. All these things here are the output pads. This interacts eventually with the pins on the chip that we're going to fabricate. Okay, so as you see here in the NMOS section, everything's symmetrical, and everything is the identical sizes. So this is the concept of unit transistors that we're using here, and we're making sure everything's symmetrical to account for the fact that there exist temperature gradients. And also at the corners, we have all sorts of unit transistors to ensure all environments for all the design transistors are identical. Now, how does this relate? This was not some random mismatch of transistors. We actually planned this out precisely. Taking a look here, what we actually started out with, this is the engineering design, okay? And then from there, we decided how many unit transistors each transistor takes. So for example, M2 needs 16 unit transistors. And then from there, we laid out, we decided on a plan on how the transistors get laid out. So as you see here, M2 gets laid out symmetrically. It's symmetrical vertically and symmetrical horizontally. So this would help you balance the design. So no matter what happens in your random process variations, the circuit will still work consistently. So essentially, these two things, this drawing created this layout design here. Okay? And the identical thing was done for all the PMOS transistors. So if you take a look here, this is the PMOS transistor structure. Okay? And that wasn't done randomly. It's impossible to have done it randomly. So we did it on, based on the plan. So we took a schematic and then laid out the PMOS transistors so that they're as symmetrical as possible. And that way we can have performance that was very, very consistent. Okay, so that about covers the layout. Okay, now the simulation, what did it look like? There's got to be a disclaimer first. I did tell you that everything works in moderate inversion, and the simulator can't be relied on for moderate inversion. So for that reason, all the simulation result just proves that in general the circuit can work. Okay, and we still have to test the actual chip when it comes back. So with that said, okay, so what happened here was you took, what it simulated was you took the supply voltage and ramped it up from 0 volts to 1.5 volts. What we have here, this is the current output. So we designed for 0.6 nanoamps, and this is a part of the circuit that multiplied it by 4. So we're expecting 2.4 nanoamps, and what it ended up being in the simulation was 2.36 nanoamps. all these all these voltages are, it represents the 0 Kelvin voltage threshold temperature. That's what the voltage needs to be to not change with temperature. And so according to our calculation, this value actually does correspond to that 0 Kelvin threshold voltage. Okay, and now, say you kept the supply voltage at 1 volt, and then you change the temperature from minus 20 to 80 degrees. What happens? Well, this is what happens. We have a 2 millivolt change from 22 degrees to 80 degrees. So that's a 2 millivolts change for 60 degrees, and about a 2 millivolt change for 50 degrees difference. So these two things are the two separate parts where one you change the current, keep the load the same, or one where you keep the load, you change the load but keep the current the same. Right? So that is how it's simulated. Now, how does it compare? That was the simulation result. But say, for example, like say we really got this in the real chip. How does it compare with everything else? Well, not exactly the best. Well, the best here was 7 parts per million per Kelvin, and the simulated performance of, even though it's only like 2 millivolts for a 60 degrees change, which is still pretty decent, is about 23 parts per million per Kelvin. And even if it were really that performance, it wouldn't be the worst one out there, right? But clearly, we do use a lot less power than anyone else. The next best one is 36 nanoamps. And the amount of area we're using actually isn't really far off from what everyone else is doing either. So, our original objective is to get this chip that doesn't use up that much power, doesn't take up that much space, and is also really accurate. So the really accurate part is the part we have to verify. Everything else should be really low power and not take up that much space. Okay, so what comes next? Basically, everything is done, and we need the chip, right? What's coming up next is early next year, we're expecting the microchip to come back. And how exactly are we going to test it? We propose to test it by, like, say, have the voltage reference being isolated from all your measuring devices. So the way to do it is put it into a unity gain op-amp here. Okay, and to vary temperature, an idea I propose, at least, is to use a temperature-controlled fridge. I saw a few of these in the biology department, by the way. And, or use an oven to go from, say, like 20 degrees to 80 degrees. And hopefully we can test the performance of our circuit that way. And also, there's got to be a noise consideration. All other designs that I've seen in literature, they don't account for noise in it. But apparently, there may be a problem, especially if you're using really low power. So what we've done so far is we sent the design to someone in Belgium, another researcher, and they're going to focus on analyzing the noise and doing the noise analysis for us, and hopefully it will correspond to what we can measure. So that is it. Thanks a lot for your time. That's the end of the seminar research presentation. And I would really like your feedback, and I want to know how this research can really be improved. So, yeah. Well, sort of. It will help from people in South America, like Dr. Rossi, and some people in Belgium. So what left? It's an international project, really. So, all right. So I guess I could stop the video at least from here.